Greetings. The objective here is to gain some simple geometric insight into the fundamental theorem of calculus, as it's called. So consider, if you would please, a function f of t, which I've drawn here. I picked a very basic function since I'm limited with what I can do here in PowerPoint. Remember that the height of the curve at any particular value of t tells you the value of the function there. So if we plug in this particular value of t, the height of the curve tells us the output of the function. And now let me pick a specific place on the t-axis, which I will call a. This is going to be fixed for now. And then a variable x. X can be moved to the right or the left. And I've shaded in the area between the vertical line at t equals a and the vertical line at t equals x. Obviously, if I move x to the right, the shaded area would increase, and if I move x to the left, the shaded area would decrease, which tells us that the area depends on x, or in other words, the area is a function of x. And that's why I've written capital F of x, so as not to confuse this function with the other function, lowercase f. And I picked these letters because they're commonly used in calculus textbooks. And many of you already know that one way of expressing that is with an integral. We know that the integral of f of t with respect to t between t equals a and t equals x, that's the area under the curve f of t. And I'm hoping to give you some more insight into why this is the case, or how to interpret it. So instead of writing capital F parentheses x, for now I'll just put the capital F, but capital F, you should attach the meaning area to that letter. When you see that letter F throughout this video, just think of the area that's shaded. Now, if I were to scoot x to the right by a little bit, just bump it over to the right by an amount delta x, obviously the area would increase. So I've highlighted the extra area that you would accumulate if you increased the value of x. And a good label for that extra area would be delta x, because if we change x, then we're going to change f. Remember, big F depends on x, so if x changes, f will change as well. Now, what is delta f? That's the area, that's the extra area picked up as we scoot x to the right, so that would be the area from a to x plus delta x minus the area from a to x, right? Just the total area, green and blue, minus the green area would give us the extra little piece of area. So the change in f would be big F evaluated at the rightmost value of x minus the original value of x. And you see, as I went between these two slides, I made delta x smaller. So if we shrink delta x, you can see that a rectangle is almost sufficient for representing the extra area under the curve. It's not perfect. If I go back here, this would definitely not be sufficient. If I made this a rectangle, we would be missing out on that little triangle at the top. But the error is not so bad for a smaller value of delta x. So hopefully you see that as you go to smaller values of delta x, this rectangle becomes a better and better approximation for the extra little piece of area underneath the curve. And since it's a rectangle, we can express its area very simply. Remember, delta f is the extra little bit of area there. We know that the area of a rectangle is the height times the base, and the base, of course, is just delta x. What is the height? Well, it's the value of the function at that point, right? The height of the curve is always the value of the function at any particular value of t, where we're looking at a specific value on the t-axis. We're at the value x. Now, you may be thinking, are we at x or are we at x plus delta x? It kind of doesn't matter, because if delta x becomes really small, then the function is essentially constant over that tiny little range if it's a continuous function. So let's use the function evaluated at x, that's this height right here, for the height of the rectangle. And this would be a valid expression then for the height of that rectangle. It's the height of the function at that particular place on the t-axis times the interval delta x, the width of the rectangle. And we could just rewrite this, solve that for f of x, And we can express it as the change in the area due to a change in x divided by that change in x. So you could, in words, you could say it's the rate of change of big F with respect to x. If you sweep x to the right a little bit, how much extra area do you accumulate? Take the ratio of those two quantities. You could say if we're talking about a strictly geometric interpretation here, area is square meters, distance is meters. So it's the number of square meters you pick up per extra meter that you scoot in x. Well, what happens if we look at skinnier and skinnier rectangles? If I make it too skinny, there's nothing to look at here, so I'll stop there. But df might be a better name because the idea is if your extra little scoot to the right is infinitesimal, if it's a number so small that you can't even assign a number to it, then instead of calling it delta x, we should probably call it dx. And don't forget that dx means really a change in x. It's still a delta x, it's just a teensy-weensy infinitesimal dx. As close as you can get it to zero. It's as close as you want to zero. So this is still the change in area. It's the extra area accumulated, and this is still the change in x, but we're using this special notation that's bequeathed to us in calculus. And that means we can rewrite the ratio up here. The height of the curve at this point, well, that would be the area of this infinitesimal rectangle divided by the width. And the area we're now calling df, and the width we're calling dx. So this is still, in a way, this is the formula for the area of a rectangle. It's just been solved for the height. And we can say that this expression, this ratio, is the limit that you would arrive at. It's really the same as delta f over delta x in the limit as delta x goes to zero. As you let delta x become an infinitesimal quantity, then so too will the increase in area become infinitesimal. They're both super teensy-weensy tiny numbers, but the idea is that when you take their ratio, you'll still get a finite number. So this ratio would approach a limit as you let the width of your rectangle get skinnier and skinnier. And this is the great insight of the fundamental theorem of calculus, or it's part of it at least. So if you've never fully appreciated it, just suppose that you had a formula for the area under this curve. It's not hard to get that formula for something as simple as a line. It's more difficult to get it if it's a parabola, to find the area under a parabola. It would be difficult to do that without calculus. But suppose you had a formula for the area under some function. And that formula is what I'm calling big F. Big F is the area formula. In summary, if by some means you have determined the formula for the area under this curve beginning at some arbitrary endpoint and ending at a variable x, all of that area, if you then take the derivative of that formula for the area with respect to x, you will recover the function that describes the curve. So take the derivative of the formula for the area to get the formula for the curve under which you've calculated the area. That's it. That is what's called the fundamental theorem of calculus. And it's not necessary to have this geometric interpretation, but for me personally, once I was able to see that, it kind of tied together this notion of the derivative and the integral. And most of the time, you're using integrals in applied math or physics, for instance. You're not necessarily calculating areas, but again, it's nice to have that interpretation. Now, the way you've probably seen this presented in a book is not with this capital F. It's this way, because remember what capital F is. Big F is the area from t equals a to t equals x, and x is the variable that you can move around. That's what this says. The integral of f of t dt from t equals a to t equals x is the area under that curve, and we are taking the derivative with respect to x of that area. So it's kind of like this whole thing is big F, not kind of like it is. This is big F. That's what's interesting about this notation. I love this about the notation. If you were to plop this whole thing in the numerator, it would be d big F over dx, which emphasizes that it's the change in the area compared to the change in the x-coordinate. It's the ratio of the change in two quantities. But when we move the d over dx out front, and then it's no longer as if this is in the numerator, you don't have to think of it that way, then d dx becomes like an operator. It's an operator that does something to a function, because remember, this is really a function of x. Yes, you've got the function lowercase f, but you've already integrated with respect to t. This is now the variable, because if you move x to the right, you're now talking about a greater area. Remember, big F is a function of x. So we're taking the derivative of that area function, and what comes out of that is the actual function enclosing the area. So there's two ways to think about that derivative notation, and I like to keep that in mind. There we go. That's the fundamental theorem of calculus. Sometimes it's presented as part one. You know, there's I guess two main ideas. So let's move on. Before we do that, remember the interpretation of the increment in area as a skinny little rectangle. This would be the height of the rectangle. This is the width of the rectangle. Well, if you multiply height by width, again, you're talking about area. So you could think of the integrand there, the whole thing, as df. And never forget, that's a little dramatic, but try not to forget that this integral symbol is really a script s. It was chosen very appropriately. It's a giant script s because it means to sum up each of these little contributions. Basically, sum up all the little areas of the rectangles. I don't know, I almost said French fries. I like to think of them as these skinny little French fries. So big F, it's the integral of the function that describes the curve between a and x. But now we have this interpretation. This is the area of one of those rectangles, which I could call df. So I'm really just summing up all the df's. And again, you can think of that two ways. You're summing up the area of all these rectangles, which I've drawn here. You can think of it that way. Sum up all the rectangles. You can also think of it this way. Remember, d means change. Every time you add one of these rectangles, you've changed big F by some tiny amount. Big F is the total area under this whole thing. Every time you add a rectangle, you've incremented big F. So just add up all the changes, that will give you the total area. It's like looking at your checking account statement for an entire month. Every day, let's say, there's a certain DF. There's a change in your balance. Could be positive, could be negative. In this graphic, they're all positive. These are all positive areas. None of these French fries are on the opposite side of the t-axis. But if you add up all those changes throughout the month, at the end, you'll have the total change. In other words, the total area that you've added. Let's just confirm that this works, even though you already know that it does. Here's an arbitrary line, and I can't write mx plus p because remember, I'm talking about a function of t. This is the t-axis. So mt plus b would be an arbitrary line, and you remember that the intercept here is b. So this height would actually be equal to b, the y-intercept. And I'm looking at the area under this curve, which is a line, a special curve, from t equals 0, so I've chosen the specific value of the left endpoint to be 0, all the way up to some variable x. X is our variable in terms of the area. And yeah, so I'm just emphasizing that the height of this rectangle here is that y-intercept, and we can use geometry to get this formula. I'm trying to show that the calculus works, so we don't want to use calculus to get the area under the curve. We want to use geometry. Well, this is just a rectangle and a triangle. We know that the height of this, well, this point right here, see how we've got the triangle stacked on top of the rectangle? We need the height of this point. Well, that's just the height of this curve. It's the value of the function f of t evaluated at a particular t equals x. In other words, just plug the number x into the function. This is the height of the function at t equals x. So now we know what this height is, it's the intercept, and we know this height. So we can just use the formula for the area of a rectangle and the area of a triangle to find the total area, which I'm calling big F. And it's got two parts. The rectangle, well, the rectangle is base times height. The height here is that intercept b, and the base is just x, is it not? X minus 0, which is x. So that's this term. Now we need to add the area of the triangle. So I'll use 1/2 base times height. So 1/2 times the base. The base is still this distance, x minus 0, or x. And then the height, well, that would be the height of this point above the t-axis minus the height of the rectangle. Do you see that? If we take this total distance and then we subtract off the height of the rectangle, that will give us the height of the triangle. And we know that the length of this whole thing is the value of the function there. It's mx plus b. And then go ahead and subtract off the height of the rectangle, which is the intercept b, and that will leave us with the height of the triangle. So all of this garbage in here is the height of the triangle. We see that the b's cancel. You can distribute, and you find that the function for the area under this line between t equals 0 and t equals x is given by this formula. And it depends on x. If I scoot x to the right, the area will go up. If I scoot x to the left, the area will go down. So this is really the formula for the area of this trapezoid. So here's the moment of truth. If our prior reasoning is correct with the skinny rectangles, now that we've got the formula for the area under the curve, we should be able to take the derivative of this formula to get back to the function that describes the curve. Well, we already know the function that describes the curve. So let's do it. Is lowercase f the derivative with respect to x of uppercase f? You can do this derivative, no problem in your head, I'm sure, because you know how to use the power rule. And of course you get mx plus b. I've just interchanged the order of the terms. So the rate at which the area increases with respect to x, what this says is if we scoot x a little bit to the right, then big F is going to increase by some amount d big F. What is the ratio of that of those two quantities? What's the rate at which f changes? Well, it's given by the height of the curve at this particular value of t. So notice it doesn't say, it's not that d dx of big F of x is mt plus b, it's mx plus b. You're supposed to evaluate the original function at this particular value of x. All this says is the rate at which you're accumulating area depends on how high the curve is at that value of x. If we were to go over here, if x were over here, do you see how the height of the function lowercase f is not as great here? Little f is smaller here, which means we're accumulating area at a lower rate. If we scoot x to the right here, we're not going to gain as much area. So the derivative would have a lower value. And you can see that because when you plug in a lower value for x, this whole number would come out smaller. On the other hand, if x was way over here, the curve f of t is much higher. So when you scoot x to the right, you get a rectangle that's a lot taller. In other words, you get a bigger df for the same dx. Plug in that larger value of x, the derivative takes on a greater value at that point. Okay, so to summarize again, big F is the area. It's the area under the curve f of t between a and x. Once you've got that formula, if you take the derivative of that formula, you will recover the function enclosing the area. You'll notice, though, it's not essential that a be located here. Previously, I was looking at the area starting from here out to some variable position x. But what if we instead started collecting area from over here at some other t-coordinate, which I will call b? The same argument would still apply. Everything in the reasoning in the previous slides would still be applicable to this new function, which I'll call big G. So big G is the area not from a to a variable x, but from b to a variable x. If you were to take the derivative with respect to x of big G, you would still recover the function enclosing the area. That would not change. So both big G and big F will give you lowercase f when you take the derivative. See that here? You can take the derivative of the formula for area f with respect to x, and that will get you f of x, or you could take the derivative with respect to x of big G. That will also give you lowercase f. And so we say that both of these functions, big F and big G, they're both antiderivatives of little f, lowercase f. They're both antiderivatives because you can take the derivative of big F or the derivative of big G, and you will get back to lowercase f. That's why they call them antiderivatives. It's the reverse operation. The only difference in big F and big G is this extra quantity of area. And I've written that here. And I've used the letter capital C on purpose because very often in the calculus books, when you take an indefinite integral, you write, the integral of f of x is big F plus c. Well, both of these functions, the area big F and the area big G, just measured from a different endpoint, both of them have a derivative equal to little f. And the difference between those functions is just this extra bit of area. So if you measured the area from a to x, maybe you got the number 10. And then you went and measured the area from b to x, maybe you get 12, which would mean that the extra area here is just 2. And it doesn't matter where you evaluate those functions, big F and big G, at any point on the t-axis, any point x on the t-axis, when you take the difference in the two functions, it would just be that extra chunk of area, which I'm calling capital C. So here is what we call an indefinite integral. Previously, I wrote limits in the integral. That was a definite integral. The indefinite integral of any function is this just has to be any function which you know to be an antiderivative. It could be big F, it could be big G as well. And the reason for this constant, arbitrary constant of integration there is to allow for, or it's to account for that indeterminacy in which antiderivative you used. Big F would work, big G would work, and that's why you have to plop in this arbitrary constant of integration. So again, this statement is true provided that this function is any antiderivative. In other words, it doesn't matter where you put your left endpoint for the integral. The area function is still going to be an antiderivative of the function that encloses the area. Okay, what's going on in this slide? See what I just did there? Let's replace this variable x by the letter c, indicating that it's just some constant, lowercase c this time. So I'm evaluating the formula for area at this particular x coordinate. I'm calling it c. So that would be the integral of little f between a and c. And now let's evaluate the area function at some other value of x over here at d. So big F of d, that's the area under the curve f of t from a all the way to d. Right? We're just evaluating big F at two different values of x. And now it's pretty natural to see that if you want not the total area between a and d or the total area between a and c, what if you just want the area between c and d? Well, that should just be the area from a to d minus the area from a to z. That's what this says, right? This is the integral of f of t between c and d. In other words, the area under the curve f of t between c and d. In order to evaluate that, all you need is to take any antiderivative, meaning any formula for area, evaluate it at d, that's the right endpoint, evaluate it at c, and take the difference. But the important point is, this just has to be any function, any area function whose derivative is lowercase f. And that means it doesn't have to be big F, it could be big G. By the way, this is also called the fundamental theorem of calculus. Sometimes I've seen this called part 2. The other part may have been called part 1, and now this is part 2. So I want to emphasize, this is true provided that the derivative of big F is lower f. As long as big F is an antiderivative of lowercase f, this formula works. And that means we could equally well apply it with big G. Big G, where we measured the area not from this endpoint A, but from this endpoint B, the derivative of big G is also lowercase f. It's another antiderivative. So you could also express this integral as the antiderivative g evaluated at d minus the antiderivative g evaluated at c. It doesn't matter which antiderivative you use.